Hi everyone, my name is Stan and today I want to talk to you about bringing distributed computing to the cloud with Apache Ignite. First, let me start by briefly introducing what Compute Grid API is. A lot of you know this already, a lot of you might be using this, but just as a refresher, Compute Grid API is a way in Apache Ignite to bring your computations from the clients to the servers. With traditional database software, how you do compute is you load the data from the database to the application, you perform computations, then you might need to write some results back to the database. In Apache Ignite, you can save this unnecessary network traffic by bringing your computations to the servers. You don't need as many resources then on the application because the server grid is what will be used to run the computations. And you don't need to transfer the data, which is a great boost to your application performance. This can be used in many use cases. In-memory data grids and databases can use compute grid to accelerate their transactional operations. They can transfer some of the data processing from the application to the server grid, thus increasing performance. Analytical applications can use compute grid when SQL is just not enough. SQL is great, but it is a declarative language and a lot of things are hard to do in SQL, especially complex computational algorithms. And there is also a whole world of high performance computing, which is all about this most complex computational algorithms that require a lot of power, and high performance computing use cases bring the power of a distributed Ignite cluster to focus the cluster resources on solving a particular computational problem. And Compute Grid is actually especially useful in the cloud because in the cloud, the latencies are higher, the network traffic is more expensive. A lot of the time, you would even have applications scattered across multiple regions, availability zones, or even cloud providers, or maybe you have a on-prem plus cloud hybrid installation. And then you really might benefit from saving on the network traffic by bringing your computations to where the data is actually stored. And this all might sound a bit complex, especially in the cloud, with all these questions of how do I write this compute, how do I deploy it, how do I bring my compute code to the servers in the cloud. And in fact, this cannot be any easier. This is real easy, and this is what I will show you today in this talk with my demo. Before we dive into the demo and before we look at the code, let's do a brief overview of what Ignite compute tasks are coded with. The central piece of the Compute Grid API is MapReduce tasks represented by Compute Task Interface. MapReduce is a two-step execution. On the first step, you execute a lot of jobs distributedly on all of the nodes of your cluster. Each job on a node produces a partial result. And on the second step, you combine these partial results from all nodes to get a final single answer and give it to your application. There is a simplified version of it called closures, and these are smaller jobs written often as Java lambdas, which just do a single thing. It's often one job sent to a single node to do one particular set of operations. And they don't need this second step of combining the results, so they are easier to use, especially for applications such as in-memory data grids. And on the other hand, if MapReduce is not enough for you, there is continuous tasks with continuous compute task, continuous mapper interface. And what this interface does, it allows you to turn your two-step MapReduce into a multi-step computation by programmatically generating more steps and building these complex pipelines and graphs of tasks. And this type of tasks can really express any complex computations that you might have. And finally, to augment all that, there is a code deployment API that allows you to bring your code to your server grid. There is a pure class loading deployment or pure assembly loading for .NET, which allows you to dynamically share the code from the clients to the servers without any manual involvement. And there is a more controlled and more flexible version called Deployment SPI, where you can create custom integrations to load the code from artifacts stored somewhere else in a network server or on your CI/CD. So now let's look at an actual app. Let's look at the code, see how the compute app is coded, validated on a laptop by running a functional test, and then we will scale to the cloud. And to help with that, we will use a service called GridGain Nebula that helps to monitor and run Apache Ignite in the cloud. Okay, let's start by reviewing our data model. The database that we will be using today is a database of music. This database consists of artists, albums, customers, artists, albums, and tracks of various music genres, and customers and their invoices. The customers are people who are buying this music on some music marketplace, and invoices and invoice lines represent the actual purchases and purchase items. What our application will do, it will find the top paying customers of our music marketplace. This is how we will do this. The compute app starts a client, and all the client does really is starts this compute task called top paying customer task. The task is actually located in the same source file. What the task does is it creates jobs for all nodes in the cluster. So it tells all nodes in the cluster to execute a piece of work. In that job, we will, on each server, scan the locally available data and find the top customers stored on that server. This is possible because we know for sure that each customer is stored on a particular server because of the affinity feature of Apache Ignite. Here, all tables are defined with affinity key equal customer ID, meaning that a particular customer and all related data will always be stored together on the same node. This means that each node is responsible for a set of customers, and thus when we find our top customers on each node separately, then we can just combine them and sort them and find the top customers globally. And this is what we will do in this reduce step. We will take our partial results, then we will combine them here, and we will sort them, and we will get the final global top customers of our service. We are ready to test this, and to test this, we will need to start a server and upload some data into it. We have a server right here. I will use Java to start a server node with a very simple configuration. I don't have a lot of memory locally on my laptop, so I'm limiting the memory here pretty drastically, but this will be enough for our first test. The server has started. Now I will use an application that uses Ignite JDBC driver and a library called myBetis to execute my startup SQL script. This is what I will do now. And the script is executed and it all seems fine. Now it would be nice to see how much data do we actually have in the server. And for that, we will use the service GridGain Nebula that I mentioned before. Now we will use it as a monitoring service for our cluster running locally. Here in my log, I have this link that I can click and will open my browser now. Let me bring it to the presentation. Here we go. Here, I clicked on the link and the connection information for my cluster appeared right here. If I click continue, the service says that it has connected to my cluster and I can just attach it to my account now. And now I can monitor my locally running cluster with this online service. Here I can see my single node. Some metrics start coming in. I can monitor CPU load, heap size. I can actually monitor any metric there is in the Apache Ignite, any metrics that Apache Ignite exposes, but we don't need that right now. What we will use is this screen called SQL, and we will use it to check how much data do we have in our database. Here in the schema, we can see all the tables that were created. And let's start by querying the customer table. Okay, we have some customers, all the information about them. And now let's maybe just see how many customers we have. And it's 59 customers. It's not huge, not bad. And now let's see how many actual items they purchased. So they purchased more than 2,000 items, which is not huge, but it is enough for us to validate our application functionally now. So let's do that. Okay, we are back to our code and we are now ready to run our compute app. I'm running my application now. The application asks for the number of top customers. Let's calculate top 10. And it gives the results. 10 of them seems about right. I actually know for a fact that this calculation is correct. And if we calculate top 5, yeah, this is the top 5 of the first 10. Okay, this is good. Our application works. If I put 0 right here, it will exit. And yeah, we validated that compute app works locally. Now, if we try to scale right here locally, it wouldn't really work. What I want is I want to load much more data. We have 2,000 purchases now. What I want is more like a few million. But I know for a fact that my local server will not be able to handle this much data. And to handle this much data and validate my app on a higher scale, I will need to scale in the cloud. Now, let's just stop our locally running server. We don't need it anymore. And let's go back to our GridGain Nebula service. Here, what we will do, the cluster is now disconnected because I stopped it. I can actually detach it from my account. I don't need it anymore. And what I want to do now is what we did first, we monitor the cluster. And what I want to do now is create a new one. And this feature of GridGain Nebula allows to start a new cluster in the cloud without ever actually running any server processes. I just pick where to start my cluster, how many nodes I want and the size of them, uh, and some settings on the data regions, how my data will be stored, and some security settings. And I put in a username and password. This username and password will be used by my applications to connect to the cluster. The first time we tested, we didn't use any security because it's more complex to set up. But Nebula actually comes with SSL security and all other best practices right out of the box. So here I'm okay with Amazon Web Services and this Amazon region. I'm also okay with 2 small nodes. We don't need more for our test. What I want is to change the persistent storage to in memory so that our test runs faster. And I need to put in a password, and don't tell anyone. My password is Ignite Summit. And we can create the cluster now. Now we need to wait for a few minutes while the cluster is being created and provisioned and configured. And in a few minutes, we will be able to use it. Okay, our cluster is now ready to be used. And let's take a look at it. Okay, we now have a couple of nodes. Good. Metrics come in. Obviously, the cluster has no data right now. And also, our applications are configured to connect to our locally running cluster. And we need to reconfigure our applications to connect to the cloud, to the GridGain Nebula cluster. And to do that, we need to go here. Here we have this connection information. We pick the type of clients we use. We use JDBC client and we use Java thick clients. Let's start with JDBC. Here we have all the information to connect an application, but what I need is actually just this connection string. I go back here to my JDBC application. I put the connection string here. And now we are almost ready to connect, but we also need to type in our login and password, which we memorized. And now we seem to be ready to connect. Mhm. Connected, we're inserting the data, and it's done. So let's validate on the cloud. On the dashboard, we see an uptick of the CPU load, showing that we actually had something done on the server. And if we go here to SQL, if we ask for number of invoice lines, okay, it's correct. And now if we ask for the number of customers, yeah, it's also correct. So the data has been loaded successfully to the cloud. Great. Now let's see what we need to do to connect our compute app. Go here to the thick client connection instructions, and it has all the information, but what I know I actually need is just this client configuration. So let's copy this part. Since GridGain Nebula comes with all the best practices already set up, and thick clients are kind of complex themselves, the configuration that we need to use is actually more complex as well. So it has SSL included, it has authentication included. We put our login information right here. And we seem to be ready to start. And we will try, but you'll quickly see that there is one more thing that we need to do. Okay, the client started, and it seemed to have connected successfully. But when we ask it for top 10 customers, yeah, we will see this. We will see this error. And the error is saying that the task was not deployed, meaning that the server was not able to locate the code to execute this task. We didn't have this problem when running locally because the server and the compute app are running in the same on the same machine. They're using the same IDE project, so they have the same code. But the servers don't have our compute code. They don't have this top paying customer task. And so we need to deploy it. The way we do this is by uploading our an artifact, a jar with our code to the cloud. Here there is a feature in GridGain Nebula that's called deployment. Here we can add a deployment unit representing our application, and then we will add a code artifact, and it will be automatically deployed, downloaded, and used on every server node of our cluster. I'll just put my compute app here. Then it's artifact. I could use a Maven, a direct link to an artifact stored somewhere, but what I will use today is I will use an uploaded artifact. And I don't have any artifacts uploaded yet, so I'll go here to the sources, and I choose a file. Here I choose a file, the build running on my laptop. Here is the build, and the file is now stored on the control center, and when we add the artifact here, add it, we click deploy, and you can see the system says the version is now available, meaning that all servers have downloaded this deployment unit, this version, with this artifact that we have just uploaded. And to check that it works, let's go back to our compute app and restart it. It takes a bit of time to establish the connection with the cloud. Now we put 10 customers. And here is our result. And if we try to do this once again, here is our result again. Okay, now we seem to be ready to scale up. Uh, Before we scale, what I want to see is how much time did my computation actually take on the servers without the added latency of the network between clients and servers. And to check that, there is another tab in the Nebula called Compute. When I go here you can see our tasks that we executed. So this last couple of tasks that finished successfully, we can see a lot of information here. And I can just pull up the task duration. And here we can see that the first task took a few seconds. The second task actually didn't take all that much, and I bet if I do this, continuously, I will see more like this number. So less than a second for the task execution. This longer task duration is probably to establish some client-server connections. Okay, now let's try to do the same thing with more data. If we go here, this is the class that we will use to generate some additional fake data. I don't have the actual people with names and addresses, but what I have is just fake customers and their fake invoices. I will generate 4,000 customers and 5 million invoice lines, and I will use compute as well, this generate data task. I'm using compute to generate the data right on the servers instead of generating the data on the clients and sending this data over the network. This is another nice application of compute, even when you're testing. So we will need to change this configuration, of course, the same way we did it for our other thick client application. Let me just copy the same config right here. And we can finally run. Okay, the data loading has finished. Let's check it out. So yeah, we can see we used compute for this, and we can see the finished task. It took almost a minute to generate. And now we can try running the compute and see how the results changed. We can just run the same compute application once again. And now if we ask for, say, for 15 top customers, how long it will take? Yeah, you can see that it returned a 15 customers to us. The total purchases numbers are greatly increased because we have many more purchases in the database now. And most of these top customers are actually our new fake ones. But we have someone who been even in the first batch. Let's run a few more tasks. Okay, and if we go back here to our compute tab, we can see, yeah, all of our computations that we ran. We can see that in the steady state, with much more data, the duration increased as we would expect to process just uh, 2,000 records. We needed less than a second, and we need almost 3 seconds to process a few million records. This can be actually further optimized with various Apache Ignite features, but that's not the point of today's demo. And so we have actually succeeded with our initial task. We showed how we can start with compute on Apache Ignite locally. Compute tasks are not complex at all. It's a few source files, and they are very easy to write, very easy to read and understand. We used the standard interface and tools to upload some test data and to run this locally. We then used GridGain Nebula to monitor first to help us with our local testing. And then we used GridGain Nebula to start a cluster in the cloud. Uh, GridGain Nebula uses Apache Ignite interfaces to provide flexible code deployment capabilities. So we were able to also deploy our code tested locally to the cloud. And then we connected to the cloud the same way we did when we tested locally. And we tested our application successfully and were able to scale from 2,000 records to millions. Thank you all for your attention today, and good luck with your Apache Ignite applications.
Dan, thank you for that. Let me bring you back onto the stage. Great, and always good to hear about Nebula, of course. But we have we're getting a little bit short of time, and unfortunately, you are a single node. I can't just spin up a Stan cluster and ask all of the questions at once. So, what I'm going to ask you to do is kind of try and give us a sort of quick answer, which is a challenge, but here we go. So, question from Jeremy: traditional n-tier architectures have for years steered us away from mixing logic and computation in the data persistence technology components. How should this thinking change? You have 8 seconds.
That's exactly the question I would like to be answering for hours. But yeah, two points here. Basically, first is for speed, it's all a trade-off, and it is a trade-off for speed first and foremost. You either send data from tier to tier if you want your architectural purity, or if end tier architecture does not give you the latency, the performance that you need, then you start processing on the data tier. The second part is it's actually a question of perspective. And if you think about it, a lot of Ignite applications are kind of the part of data tier, really, in the grand scheme of things. The application which would access the data in Ignite directly and run this compute would be a backend for other applications and would be sort of a middleware. And why that you aren't even breaking the NC architecture, maybe. Hope that answers it.
Good answer. Now, I'm going to do some job stealing on the remaining questions. There is one about comparing compute with RDBMS, but we're not going to ask that one because I'm going to plug our new compute grid training, which will answer that question. So if you have a question about comparing stored procedures with compute tasks, please book yourself into the next compute grid training, which is the new training we released yesterday. And then all that's left is for us to choose one of your final questions. So I think I'm going to go with this one. How long should a compute task be? And I mean, is it okay if a compute task runs for hours, for example?
Uh, yes, it is. Basically, and these are sort of different worlds, really. On one hand, there is a lot of applications out there which run very simple tasks, very simple closures, which are usually just a single job doing one simple thing, and they would run milliseconds, maybe even sub millisecond. And on the other hand, you have full scale, high performance computing use cases where a single compute task could be a very large analytical problem that is running. No, I don't know. It could run for days, uh, creating new jobs for itself. So it's all of the spectrum, and compute grid is this nice tool that is useful in a lot of applications like this.
Good. Okay. Stan, thank you so much. Thanks for joining us. Thanks for your talk.